Our next speaker is Cheng, near resonant approximation of rotating Navier-Stokes equations. Let's see if I can speak that.
Yeah. So first, I'd like to thank the organizer for the invitation. Today, I will talk about essentially a PDE talk, which is in the same spirit as the last one. So it will be very idealized. You can even think of this as some model in a vacuum where the Earth is flat. Yeah. So, but I would like to use this idealized model to hopefully shed some light on the concept of near resonance and what we can do about it. So first, I will set up the problem in a more mathematically formal way, where you will see that there will be some sub-level set popping out, and we'll have to consider the integer point counting inside that sub-level set. And then this part is how I define the near resonance approximation. I use the set from above to restrict the convolution in the bilinear term. Okay, that's how I obtain a near resonance approximation. And in the result part, I will show that under some suitable condition, the proposed approximation is globally solvable and actually unique. And this is in 3D. So the 3D Navier-Stokes equation does global solvability is not known yet. But here we can show that the approximate model enjoys that property. And the second part of the result is to give an error estimate between the approximation and the original Navier-Stokes equation with rotation. Essentially, both combining both results, I can say that in the nearby the dynamics of the original Navier-Stokes equation, there's one that is close enough but also globally solvable. And yeah. That error estimate is inversely proportional to the rotation rate, which is expected. So third part, I'll briefly talk about some motivation where you can see that you can switch between two perspectives. One is asymptotic way of thinking, the other one is non-asymptotic. And then I'll make some remarks. Now I will set up my domain to be a flat torus, hence the flat Earth, and it's in 3D with arbitrary dimensions. The last one can be normalized to 1. But for the most part of this talk, I will just assume we're looking at a cube, isotropic cube, even though they can be arbitrary. The rotating Navier-Stokes equation is here, is very well known here. Coriolis Parts. Thankfully, I don't have to explain this. Yeah, was very well explained in the last talk. Here, J is the rotation matrix. You can see that it's rotating the horizontal velocity by 90 degrees, and the third one vanishes. Omega is proportional to rotation rate. And so omega is large, more or less in a large scale Earth. The value is about 10, but definitely not infinity in all applications, so nowhere near. So you push omega to infinity. That's a theoretically beautiful approach, but you might lose a lot of information by doing so. Okay. So this Surrey projection is basically projecting any velocity field in 3D onto divergence-free subspace, and by conjugate J with this array projection, you get an operator L, using which I can make the rotating Navier-Stokes equation slightly shorter, where the bilinearity is basically the original one, the advection together with the array projection, and this part is a large rotation times the linear operator L, which I defined here. So that's equation 1. Equation 2, our near resonance approximations take actually identical form, except I just added tilde. So the key difference is how I define this big tilde here. Hence, I will modify my dynamics. So I'm going to pick up a whole set of resonances based on the following idea. Okay, I will retain those interactions in the tilde. So the exact resonance here, I skipped some basic part. Basically, this is the two input wave vector k and n. So if you look at B here, you can do Fourier decomposition. Write U in terms of a series, and then of course the wave vector tells you what modes you are picking out of the two input velocities, and then k plus n obviously is the output mode, the wave vector of the output mode. And the exact resonance insists that for the input mode, the sum of the dispersion relation should be equal to the dispersion relation of the output mode. Okay. Now, why don't we relax this notation? Yeah, because this is a very, very strict equation. Here, I relax it to an inequality so that I'm looking at a neighborhood of 0. Okay, so rather than exact cancellation, I allow a little bit error. So this fuzziness here, I use a sort of delta to measure that, and I can call it bandwidth or whatever you like to call it. For the rotating Navier-Stokes equation, this is the dispersion relation given a wave vector k. So that's vertical wave vertical wave number divided by the length of the wave vector, and has plus minus sign. There's no neutral sign here. And this basically is the initial waves. Dispersion relation of inertial waves. And then define f of k as this difference here between these three dispersion relations for fixed n. Then essentially we spend a lot of time looking at this localized sub-level set. Okay, localized in the sense that I require the length of the wave vector be inside the annulus between an interior radius and exterior radius, and I require the value of this combination to be within the bandwidth. Okay, so these two sets combine to a localized sub-level set for f, and then I only look at integer points because I'm on a torus. So by starting integer points k satisfying inside this set, and then you can divide the corresponding n and k plus n. K basically corresponds to the nonlinear interaction of modes that are retained in our model. Okay, counting these integer points is crucial in nonlinear estimate of B tilde, which is the approximate bilinear term. And so mathematically, this basically goes to the calculus inequalities in function analysis. But I think physically, it also tells you how crowded or how active the nonlinear interaction is happening within this bandwidth. Okay, and the reason why we set this bandwidth about 0, because remember before, historically, people like to look at exact resonance where they're just looking at f of k equals 0. Okay, now we're widening that neighborhood, and therefore retain more interaction. The challenging part, not just for mathematics, but even for the intuition here, is that if you want to get upper bound on the number of integer points inside the sub-level set, and or look at the measure of the set in a continuum without that 3, you actually have to look at the lower bound of f, right? So the flatter f is, or the smaller f prime is, the larger sub-level set is. That's quite easy to visualize. If you have f prime to be 0, you have a constant, then everywhere you are in the sub-level set, assuming the constant is 0, or somewhere between delta and minus delta. And in mathematically, the lower bound is actually a lot of times trickier than the upper bound. Yeah. So I think in turbulence, there's, I forgot the exact name. They study some number, and sometimes just one side of the bound is easier, and the other side is very difficult. Okay, so that's the challenge we have to deal with when studying the integer points in this set. And for rotating Navier-Stokes equation, I can make this more transparent. This is basically also of them is the dispersion relation of the initial waves. They have plus minus signs, and k plus n obviously is the convolution condition. They involve square roots, quite complicated, and there's no convexity, no obvious convexity, because I can take any plus minus signs here. And there's also some degeneracy coming out, which I explain right here in these 3 pictures. So here we are looking at the same f of k with different sign combination, I don't know which one, but at different levels. Yeah, so we have 3 different level sets here for the same f of k, and these are the values. Yeah, they are kind of close to each other in a way. N is fixed. Yeah, so here n is fixed. And the red dots and also graphs are the same. They represent the same stationary point of f of k. Now, if you vary the values for the level set, you can see you have basically something disjoint and then tangent, and they merge. So you are experiencing a topological change here. Moreover, in the middle one, you have a tangent singularity here, in the sense that mathematically this is not even manifold, right? So if you insist on studying a level set, these are the things you have to encounter. But we're not studying level set, we're studying sub-level set. Right, so let me make more transparent of what I mean by B tilde. So the original B is writing at this convolution form. Well, it's a double sum form, but I think because familiar with for analysis, what comes out is e to the kx plus e to the ikx plus e to I mx, so k plus m, which is output wave vector. And this is true for any linear term. The approximation here is that in this double sum, I restrict my k and m, the input wave vector, to the near resonance set n. Okay, so the near resonance set n has the membership is 3 wave vectors, but the third one is basically comes from convolution condition. So what is this n here? This k is defined in here, where I use a triplet value, which is basically the combination of 3 dispersion relations with signs here, sigma 1, 2, 3. And you look at all such triplet nkm from the integer points, from the set of integer triplets of these 3, those 9 integers. And then I require that the minimum of all such omega subject to changing signs is less than or equal to a preset bandwidth, which depends on the wave vectors as well. And then this is the convolution condition. So if I set the bandwidth to be exactly 0, then actually we are looking at the exact resonance. Okay. So now, of course, we have to impose some condition on the bandwidth. Otherwise, if the bandwidth is too wide, you are basically covering the original linearity. Therefore, you're just studying the original Navier-Stokes equation. Here, I require that the bandwidth up to a slight modification, yeah, in case like 1 over the length of the wave vector, up to a universal constant, then the near resonant approximation 2 of the original Navier-Stokes equation, equipped with any initial velocity field, yeah, it can be arbitrarily large, and in any HS space, which is a sublet space. All such things, and actually in any torus with any dimension, yeah, L1, L2, L3. Then for such system, you can find a unique solution that exists for all times, all positive times in the same regularity space. And of course, you can bootstrap here to any regularity. Yeah, this kind of smoothing property we encountered in this morning's talk. Then now, if I reverse this direction of the inequality like that, then I can see that the approximate solution U2 and the original Navier-Stokes solution U, the difference is controlled by the difference in initial data, obviously, plus a constant times something inversely proportional to the rotation rate. So the faster you rotate, the closer my approximation is to the original solution. And S prime here is at least a 3 derivative less than the original S. So that's due to some cardinality and the PDE estimates. And importantly, the constant C here is independent of the viscosity and the rotation rate. So I'll make a remark here that all estimate depends smoothly on the dimension of the torus, whereas if you use the exact resonance approach, that's not the case. That's never the case, because there's so-called small divisor phenomenon in that kind of analysis. Right. So the motivations here are the following, make very brief. So Chauchet in the 94 paper proposed this following transformation. Well, this transformation is known for many years. Yeah, just you have a principle. You linearize things around background state, and you get a linear term, large linear term, and then you do this uniform unitary transformation, which will rewrite this system into one without the large term, and then you can take limit, yeah, on that solution. That limit exists. That's the first part of Chauchet's work. And this is, in his work, this is a hyperbolic system. So, so the solution, the validity of the work is on a finite time interval. The second part of this result is to actually identify what the limiting dynamic is. Yeah, of course, I mean, there's always some limit there, but what PDE or what kind of equation the limit is satisfied? Well, it satisfies this very simple one, except the bilinear term actually is defined in this way. This is the infinite time average of this nonlinearity where you evolve backward on the input parameter and evolve forward on output. But the input here, W, is fixed and it's not does not play any part in the time integral average. Okay, so if we write this out for the Navier-Stokes system, then you can see that in this infinite limit, all that's retained in those double sum convolution is delta equals exactly 0, exact resonance. Right. There are also other work on basically geophysical models. This one is on rotating Navier-Stokes equation, and recently this one is also on Navier-Stokes but with fractional Laplacian. Again, we saw this in this morning's talk. I want to make a remark that very interestingly, yeah, this 2018 work actually is examining more carefully on the counting problem for the exact resonance set of fast type, which means that all three dispersion relations are non-zero. And the restricted wave numbers, yeah, in annulus like this, then the upper bound, yeah, for that type of integer point satisfying exact resonance is radius r raised to 1 plus any arbitrary small epsilon. So that's really small because we are in a 3D domain. So the full counting for all the interaction inside this annulus is r cubed, and this is really small. So which is why I think only studying exact resonance will just lose too much information compared to the original nonlinearity. In the non-asymptotic approaches, this near resonance notion, as far as I am aware of, we are aware of, first appeared in Wells' work. Interestingly, he said that if you use near resonance approach, you can see that they contribute to some large scale features such as zonal flows, which, for example, the zonal just on Jupiter we've seen earlier. There are other, successive works to argue that this kind of contribution is important in other structures. Now, numerically, Holt and Wingate in 2014, they use a finite and a discrete version of Chauchet's formula here. So they put, obviously numerically you have to use a finite time t, and also you have to discretize this inequality. What they find is that if you use this finite and discrete version of Chauchet's formula, and actually apply to GFD system a la Emmy Maida, then it serves as a very cost solver of a parallel algorithm that perform really well. So this further shows that numerically, if you can capture enough near resonance, then actually that algorithm captures your actual dynamics pretty well. So my remarks here in the last slide. So this novel approximation strikes a balance between retaining a large set of nonlinear interactions and global solvability, given that we don't know the global solvability of the full Navier-Stokes equation. But here we give a criteria saying that, oh, if you retain this much interaction, then surely the system is globally solvable and also stays close to the origin system. And we, of course, widens the strict zeroness to a fuzzy neighborhood of 0. And by doing so, when we do the study, when we look at the modes inside the set of interest, you're no longer studying that Diophantine equations. Yeah. This one has some unphysical sensitivity to perturbation in domain geometry. Basically, if you think about this following equations, y minus cx equals 0, and you think about c in the set of rational number and c not in the set of rational number, you can figure out how many integer solutions there are for either cases, but we know that rational and irrational numbers can be arbitrarily close. So that's what I mean by sensitivity, not very physical. Then by studying near resonance, we are studying Diophantine inequalities here, and it's very robust. And against this kind of geometric perturbation, and there's no need for very heavy number theoretical lifting. But one thing I would like to further explore is this approach in other geometries, especially on spherical domains. And in that case, one natural thinking is to use spherical harmonics, but that actually doesn't have that much convenience, as convenient as free analysis and the torus. We have two papers on archive, and this one actually is on rotating Gaussian equations, which has more intricacy than the rotating Navier-Stokes equation. So you're welcome to check them out. Thank you.
Yes, thank you for the very interesting talk. So I have a simple question. Like when you have like, let's say a near resonance condition.
Yeah.
So you specify the delta function.
Yeah.
So then the nonlinearity that you would select, does it satisfies the cancellation property or the energy preservation?
Energy, yes, for sure.
It will.
Yeah.
Okay, so now I have another question based on that. There is a 2016 results of Teritao, which you probably know.
2016 or 16?
2016 result of Teritao. So it proved that if you want to, like, you modify the nonlinearity so that you have the cancellation property satisfied. I was not talking about near resonance.
No, I think I know that paper.
Yeah, you know the paper. So it proved like when you time blow up for this modified nonlinearity.
Yeah. So
how do you reconcile the two?
Well, that paper is one of those things that caught our attention in sort of thinking that if you manipulate nonlinearity, the resulting system may behave, kind of in different ways. So he used a quite different approach to modify nonlinearity.
Yes.
Yeah, therefore resulting in blowout.
So the idea is here, like instead to focus on like the good set of modes that would be like interacting while having global solvability.
I haven't got quite understood the physical motivation behind his approach. I mean, there's the invariance and symmetry stuff that he used in further. So I guess in our case we're mostly focusing on rotating fluids and the inertial waves, which is physically known. I think, in fact, people study the inertial waves inside the Earth sometimes, not just in the atmosphere. So based on that, we try to select the interactions within B, which confer to this inertial wave interaction. So that's probably the main motivation why we use this to study this. Yeah.
In that sense, what you are proposing is like more physically motivated.
Yeah. In the Gaussian nexus system, the waves are inertial gravity waves, which is well known. Yes.
Can you explain why in your approximation you can get the global existence?
Yes, thank you very much. It's because the counting here maybe I will look at this one. So a sufficient condition for global stability is that if the count is no greater than R squared. Okay, the full counting is R cubed in 3D. If you're counting, the number of interactions is R squared, then the nonlinear estimate behaves like 2D. And we know for 2D, Navier-Stokes equation is no, everything is no. So yeah, that's essentially it. It's just that if you use exact resonance, actually this can be much smaller. That's why they are able to use fractional Laplacian in this paper, which is quite remarkable. Yeah, that's it.
Okay, so I have a follow-up question. So, I mean, because you do this restriction of the approximation of the nonlinear term, you get a better estimate on it, and that's why you get global existence. You get somehow lower Sobolev norms, and then the rest.
Yeah.
Okay. Okay.
It works also for any initial data, or it's also the initial has to be sufficient as well?
No, any initial. Basically, it behaves like two-dimensional Navier-Stokes equation. But I have to emphasize that the interaction are fully 3D. There's no apparent two-dimensional reduction or anything like that, or decoupling. You know, sometimes people would see decoupling of the vertical and horizontal direction. I don't know, because it looks like can be anywhere. You can qualitatively use MATLAB to see where the interactions are. So it's fully non-linear, even though you can see that for inertial waves, horizontal mode, yeah, K3 and N3 being 0 gives you the no waves, yeah, to zero frequency. That's a trivial resonance at 0, 0, 0. But once you start opening up the bandwidth, everything's 3D. Only the counting behaves 2D. So that's what I'm trying to argue here.
Okay, so let's thank the speaker again.
Thank you.
Okay, so we have some announcements. So one announcement is tomorrow, Amit Apte will not be able to speak because he got lost in the visa process, and so he cannot come to the UK. So